We are going to learn about geometric series or exponents. Geometric series is the expression for the sum of terms of a geometric sequence such as this: 1, 2, 4, 8, 16, and so on. Can you see the pattern here? What does 1 stand for? These things can be represented as, we all know that 2 raised to 0 is 1, 2 raised to 1 is 2, 2 raised to 2 is 4, and so on. If you follow that pattern, this is what it will look like: 2 raised to 0, 2 raised to 1, 2 raised to 2, 2 raised to 3, and so on. There is a special word in mathematics for this. That is called exponents. Exponents is nothing but multiplying various numbers by itself, such as 2 raised to 3. The 2 is called the base and 3 the exponent. When you have 2 raised to 3, you would say 2 times 2 times 2. If it is 2 raised to 7, it will be 2 times 2 times 2 times 2 times 2 times 2 times 2. That is, you multiply 2 by itself 7 times. This can work for any series. So you could have 5 raised to 2, 5 raised to 3, and so on. See, if you can see carefully, the base is always the same, that is 2, and the exponent would vary in a geometric series. In the last slide we saw how they changed. They went out from 0 to 63. In order to find the sum of a geometric series, we use a concept called the common ratio. This is an idea we need to learn along with exponents and base. The common ratio is nothing referred to as R. R is a ratio. That means you divide the first number by the second number. In this case, it is like 2 raised to 1 divided by 2 raised to 0, which is 2 divided by 1, which is 2. So in this geometric series, the ratio is, common ratio is 2. We will use common ratio, exponents, and other things we learned about geometric series to find the sum of geometric series. The sum of a geometric series is basically adding up all the numbers: 1 plus 2 plus 4 plus 8 plus 16. Let's say we want to add all the way to 2 raised to 60. Could be any number, it doesn't matter. The way we identify the sum of them is sum, which is that red sign which looks like an inverted E, which is a Greek letter for sigma. In Greek, ancient Greek, they use sigma to denote sum. We will say 1 plus 2 plus 4 plus 8, they will say sigma of the first 4 numbers, 1, 2, 4, 8, and so on. Now we want to keep adding all the numbers from the first to the second last one. Now here the ratio and is defined as A1 times 1 minus R raised to n over 1 minus R. If you notice here, R raised to n is also an exponent, where R is the base and n is the exponent. R is a number that we multiply by itself many times. R is nothing but the common ratio which we just found in the last slide. In this case, we found it is 2. A1 is the first number in the series. So in our series, specific series, it is 1. So A1 is 1. R is 2. And the total is 64. Sigma, like I mentioned earlier, it means sum. If you use this formula, you can find out the total amount for this geometric series, which, if you were willing to add them all on your own, would take many, many days. Hope you've learned something fun today. One such example of using a geometric series is in chess. In ancient India, there was an inventor called Caesar who invented chess. He took it to the king, and the king was so happy to see such a lovely game that he offered him anything he wanted. Caesar offered a grain of rice. The king laughed. He said, "Just a grain of rice?" He said, "Yes, 1 for the first, double it for the next location on the chessboard, and so on and so forth. The king laughed and he said, "You could have asked for anything and all you want is a grain of rice." Caesar smiled. Using the geometric series calculation sum that we have found now, if the king would have given him rice, it would have come to more than 18 trillion grains of rice.